Hello and welcome to my video. Today I'm going to be giving you a demonstration of my parallelized Word2Vec LLM encoder. Let's get right into it. First, we're going to need a couple of things, the big one being your jar. The second being your input. Now, how do we determine our input in the first place? I went with some very general historical books, specifically a children's history book and a general world history book. One, because they're going to cover the same topics, and two, they're going to be so general that we're not going to get very specific vocabulary from one particular time period or one particular place. Next, we have to figure out how we're going to shard it. For this particular Word2Vec configuration, which I'll get into later, I decided shards of 100,000 words would be best for our window size as well as our number of epochs and just for general parallelism. So in total we've got 14 of those, 1,400,000 word shards between these two texts. And that's really all we need. Oh, and a bootstrap, but I'll get into that later. So first let's hop into AWS. Here is, you know what? We'll go into this first. I'm going to clone this so you can I can show you that it's happening in real life. It's not pre-recorded. Here's my bucket, no outputs or anything like that. But now I'll go into the specifics while it's running. It takes a while. So first let's clone this so we can see again what exactly was I even doing to begin with. So after I uploaded my jar, my input, and my bootstrap, I had to configure some settings for the cluster. First, we're obviously going to be using Hadoop on Amazon Linux. These were provided to me here by default. I went with them. Changing them required me to ask for a new quota or pay for something. Not doing all that. Let's move on. So how do we determine how many clusters the size of our clusters, how many instances do we actually need? I said, you know what, Amazon? You handle that. 2 to 20 is probably good. Obviously, we have 14 shards. We could probably provision 14 instances, but each one already has multiple cores in it, so Amazon can take the wheel on that if they decide they can't handle it on only 2. I already did another project on AWS, so I'm using the same virtual private cloud and subnet as I did on that one. Nothing too crazy here. Now, whoa! What is this? Two steps, but Dylan, you only had one jar. Now see, what's going on here is a 2 girls, 1 jar situation. Let me explain. So in this jar, we have a driver that contains both our Word2Vec and our cosine similarity operations. And what we're going to do first, in the first step, is Word2Vec. So what does Word2Vec even do? A couple things. First, we're going to use JTocket to encode all of our input to the same byte pair encoding. This is what we're going to pass as training data to Word2Vec. We could do the defaults tokenization factory, but then when we're getting the data later, each one is going to have a different ID. Just a pain to keep track of, so for our sake, we're going to keep one ID for every word. So how do we actually configure Word2Vec? Well, first, because we're using byte pair encodings produced by JTocket rather than Deep Learning 4J's default tokenization factory, we have to set up our own tokenized sequence iterator. That's what's going on here. This is our own sequence iterator based on their interface. This is what allows Word2Vec to go through each of our sentences that has already been converted into tokens. Usually Deep Learning 4J would use one of their libraries for that. This function split array on token, we know ahead of time that the byte pair encoding for a period is always 13. So in order to divide up all the windows into sentences consistently, we just pass in 13 as our separator, and we turn a long array of ints into a list of smaller sets of arrays of ints. Then we train, and that's really it. After we train all of our separate shards, we're going to collect them, and we're going to aggregate them. Now this happens fairly quickly because we've parallelized the operation, and the reducer just has to take the averages that it produces in the output. Let's see, is it still running? let's check on the progress. We're still in the bootstrapping phase. See, this is why I wanted to start it ahead of time. We haven't even started the steps. Oh, this is actually a good time to tell you. So what is the bootstrap? So the bootstrap, it's a little bit complicated. If you're using Deep Learning 4J, it requires an ND4J backend. Now, even though Deep Learning 4J is in Java, this backend has many libraries written in C and requires shared object files in your environment. Even if you put them in your project, they need to be configured for your environment. So, what's going on here? Chances are Amazon's EC2s don't have this particular shared object file that it's looking for. They don't. So what we're going to do is we're going to install it. We're going to find wherever it installed, and then we're going to say, all right, if you're looking for this particular file, it's over here. I compiled this on Ubuntu Linux, so I was looking for, my jar is looking for libopenblast nolapack. Amazon's EC2s are on Amazon Linux, and so they're going to be looking for libopenblast.so.0. This bootstrap downloads that library, and it says, hey, you're looking for libopenblast nolapack, it's over here. And even though it's not really the same thing, it is the same thing. That's what the bootstrap does on every single EC2 that Amazon provisions for us. Because without this shared object file, the backend will not run and Deep Learning 4J will not run. Figuring this out was a hellish 2 days. But in the end, we were able to not only build for AWS, but also locally. This applies to if you're using a Mac or anything, you would just change it for the file name, the appropriate file name. Anyway, so what happens after we do our MapReduce? Well, we're going to create an output file with all of the embeddings. I would love to show you that, but it hasn't finished yet. But then, after we have all of the embeddings, we're going to go through every single one of them to find the closest word pairs, which is what the cosine similarity MapReduce does. Now, the name is a little misleading. Even though you might see word embedding mapper and cosine similarity reducer, this is the furthest thing from a parallelized operation that you could possibly get. The mapper reads everything and into a single key, and the reducer reduces that single key. This is single-threaded. There's really no other way to do it, though, because if you're comparing every single word to every single other word and you split them up into shards, well, what if the closest word in this shard is actually over in this shard? You just can't do it. Well, maybe you can. I'm not smart enough to know that. And this works. It just takes an extended amount of time. So after it goes through, it looks at every single word embedding and compares it to every single other word embedding using a dot product. And that's really it. So let's view the progress. Still no logs created yet. Wonderful. Let's examine our node status. It says we're running. We're no longer bootstrapping. This menu here is a great way to find out absolutely nothing, but it's very interesting to pass time. Refreshing all of these. I guess we could get into the experimental aspect of this. Let me bring myself over here. Teleport. So how did I land on these particular settings for the Word2Vec builder? How did we choose minimum word frequency of 5, layer size of 100? ChatGPT. No, the actual answer is this data set that I'm working with. In order to maximize parallelism, I thought 100,000 words would be just enough to have enough data that it's meaningful, but not so much that we're getting a whole bunch of gibberish that's going to take forever. Especially since we're only using a minimum word frequency of 5. If we decide that the entire text is going to be a shard, we're going to have a whole bunch of words that really shouldn't be part of a vocabulary, yet they're thrown in there just because they happen to be seen at least 5 times throughout all 1 million words. But 100,000 words, for the most part, vets out a lot of that nonsense that really doesn't need to be in there. Layer size 100. I went with 300 originally and got some nonsense. Might have also been because I only did one epoch originally, so it was trying to come up with 300 comparisons to make, but only on one pass. I decided to up the amount of passes to 5. We're parallelized, we can get away with that. But I shrunk the layer size down to 100 because we really only have 100,000 words. And any more than that, there's not enough relationships to be had in that few amount of words, honestly. Seed 42 was the default. Window size 8. The default window size was 5. For a history book, a lot of the sentences were longer than that, with complicated relationships in individual sentences, describing historical events. I bumped it up to 8 just to be safe. And that's really it. A lot of guesstimation, a lot of, welp, it takes me an hour to upload this file, so messing around with it anymore is just not worth my time. So anyway, let's see what's going on in AWS. Should I be surprised? I don't think so. God! Yeah, okay. I'm done with this. Alright, let's see. How we doing? Should I be surprised? Should I even be surprised? In the meantime, so who are you voting for? Leave your answer in the comments. Yo! Wait. We actually did something. We did something of consequence. Let's take a look. So in the bucket, perfect, we have an output. Now this isn't actually the end, because we've got 2 steps, remember? But let's see, what did this output create? Why is it choosing to... There we go, that's better. So let's take a look at some example words here. We'll skip past all of the junk. Look at that, we got Richard, river, the ID, how many times we saw it, and then the actual embedding. Now I don't like that we see some of these having a frequency of 1 when I specifically said that the vocab had to show up a minimum of 5 times. Other jobs starting. Okay, cool. Yeah, it's running the cosine similarity. This one's going to take the longest, because again, this is just one reducer doing an O of n squared operation, comparing every single other embedding. Is this the best way of doing something? Probably not. Is there a more intelligent matrix style solution? Probably. Am I going to write one? No.
2 months old has become the call sign for a world needing distraction and finding it cute, moist, and unbothered. Whether she walks, eats, plays around, anything Muding does gets a reaction. Get enough and they keep coming. Ties and tourists of all...
Finally. Let's check out the bucket. Pairs! Alright. Download. So, let's see. Is question mark similar to question mark? Yes! Very good, very good. No, these aren't really These aren't really that great. Let's scroll down to get some more full words because some of these are partials. Skip past all. Yes, numbers, very similar to other numbers. Wife terrible. Oof. What else do we got? A tough tribe, perhaps. Together they. Yeah, yeah. Now I've had some better ones doing this, so let's see. Body. A football team. Teaching disciples. This one should be, this is cut off of Socrates, so we've got Socrates and teacher there. That's very interesting. Sun is in the sky. Very cool, very cool. Go and teach. Yeah, I could see that. Settlements America, yeah. Race and peoples. Okay, railway lines. Hey, there we go. Prison and captured. Yeah, there you go. Anyway, that's all I got for you. Sorry it took so long.